Welcome to another video lecture series on linear integrated circuits. I am Dr. Vinod. So in this video, we are going to discuss about the emitter coupled transistor pair. It is also called as emitter coupled pair. So here you can see an emitter coupled transistor pair circuit which consists of two transistors, right? The one is Q1 and Q2 whose emitter are connected together. That arrow mark is represent the emitter, which are connected through together through a common resistors or a current source. Here the current source I have used and its values IE. It is also called as a differential pair, and it is widely used in the differential amplifier and operational amplifier. So you can see the V1 I have given to the base of the two transistor Q1 and Q2. IC1 is the current flowing through the two collector of the transistor. Okay, so this is a simple multiplier using a emitter coupled transistor pair. So as I have told you, it consists of a transistor Q1 and Q2 which act as a differential amplifier. The input V1 is given to the differential amplifier circuit and the input signal V2 is given to the emitter coupled differential pair through a current source to the constant current source. So thus the multiplier circuits provide the output at the two quadrant only. So here I have used two identical transistors Q1 and Q2. That is the beta value is same. So and their emitters are connected together. The inputs are applied to the base and the output is taken at the collector terminal. So therefore the output current IC1 and IC2 are related to the differential input voltage V1, which is given by del IC, that is equal to IC1 minus IC2. I can write from the figure A, IE is equal to IE1 plus IE2, right? So we know that IC1 is equal to IE1, that is equal to IS into e power VBE1 divided by eta into VT minus 1. So this I can approximate into IS into e power VBE divided by VT. If I take eta is equal to 1 for a silicon made transistor. Okay. And in the similar way, I can write IC2 that is equal to IE2 that is equal to IS into e power VBE2 divided by eta into VT minus 1. If eta is equal to 1, I can write IS into e power VBE2 divided by VT. Here, IS is nothing but your saturation current and VT is thermal voltage that is equal to KT by Q, right? So from the figure I can write V1 is equal to VBE1 minus VBE2, right? So you substitute that value. So IE divided by IE1 is equal to 1 plus IE2 divided by IE1. This is from the equation 2. If I divide the equation 2 by IE1, so you substitute the value of IE2 and IE1. So therefore I will get 1 plus IS into e power VB2 divided by VT divided by IS into e power VB1 divided by V. So here IS and IS get cancelled out. Therefore I will get 1 plus e power VBE2 minus VBE1 divided by VT. Right, because e power x divided by e power y is equal to e power x minus y. And I can write this equation is equal to 1 plus e power minus V1 divided by Vt from the equation 5. Okay. So what I am going to do, from this I can write IE1 is equal to IE divided by 1 plus e power minus V1 divided by Vt. So this is my sixth equation. If instead of IE1, if I divide the equation 2 by IE2, I will get IE divided by IE2 is equal to IE1 divided by IE2 plus 1. So that is equal to Is into e power Vb1 divided by Vt divided by Is into e power Vb2 divided by Vt plus 1. So now I'm going to substitute this IE2 value and IE1 value. This is similar to the previous values only. So the IS and IS get cancelled out, and the e power term, if it goes up, means you will get 1 plus e power Vb2 minus Vb1 divided by Vt. Right. So instead of e power Vb2 minus Vb1, here I am getting e power Vb1 minus Vb2 divided by Vt. Right. This is the only change. So I can write this one as IE2 is equal to IE divided by 1 plus e power V1 divided by Vt. So instead of e power minus V1 divided by Vt, I am getting e power V1 divided by Vt. And you know that del IC is equal to IC1 minus IC2, that is equal to IE1 minus IE2. So I am going to substitute that 6th and 7th equation. So del IC is equal to IE divided by 1 plus e power minus V1 divided by Vt minus IE divided by 1 plus e power V1 by Vt. So if I take the IE common, I will get 1 plus 1 divided by 1 plus e power minus V1 divided by Vt minus 1 divided by 1 plus e power V1 divided by Vt. Right. So this I can write it as IE into tan H V1 divided by 2 Vt. So this is approximately equal to del IC is equal to IE into V1 divided by 2 Vt. So this figure 2, it shows the DC transfer characteristics of the emitter coupled pair, where V1 is less than Vt. We can approximate this equation. So the maximum value, you can see it goes to IE, right, del IC with respect to V1. Okay. So the current IE is a bias current for the emitter coupled pair. So if the IE is made proportional to the second input signal V2, then I can write IE is equal to K into V2 minus VB on. So if I substitute this A value in the B value in the A, I'll get del IC is equal to K into V1 into V2 minus VB on divided by 2 Vt. So this arrangement is shown in the figure B as figure B as a simple modulator type multiplier. Okay, so this it can be used as a multiplier provided the V1 is small and much less than the 50 millivolt and V2 is greater than VB. So what are the limitations of this one is the V2 is offset by VB on, and V2 must be always positive, that is 2 quadrant, and tan Hx is approximated as x. Okay, so the first two limitations are overcome with the help of Gilbert multiplier. So what are the applications of this emitter coupled pair? It is used in the differential amplifiers, operational amplifiers, comparator circuits, communication systems, and analog signal processing. So here why it is called as emitter coupled means both the emitter of the transistor is directly coupled through a common path. So what happens if a differential input is applied? So if Q1 is increasing means compared to Q2, it will conduct a more current and Q2 conduct a less current. So this voltage drop occurs at the collector, the resistor will change. So the differential output get produced. So if suppose if I apply both input are same, so the both transistor will conduct equally. The collector current will be equal. So the output voltage becomes 0. So what are the main difference when compared to the Gilbert multipliers? The emitter coupled pair amplifies the difference between the two signals, and it uses differential amplifiers, and it uses a single differential input, and it has a limited linearity for multiplication, whereas a Gilbert multiplier it provides better linear multiplication. It has two differential inputs. It multiplies two input signal, and it is used as a multiplier or mixer. So I hope this video is useful for you. In order to view the lectures on the linear integrated circuits, you refer to my previous videos. Thank you.